Okay, our next lesson here is on the inclined plane. So an inclined plane is just a ramp. Let's imagine that we have a person standing on a ramp on a bathroom scale attached to a rope, and let's imagine that we increase the angle. And the question is, what's going to happen to that scale reading? Well, you can see that as the angle increases, you can consider the really extreme case here of a really big angle, I suppose. As this happens, there's going to be more of the person's weight on the rope and less on the scale. So we expect the scale reading to decrease because there's more weight on the rope and less on the scale as the angle increases. I've wanted for years to build this apparatus, but just haven't found a decent place to stand it up. Okay, so the next question we've already answered. As the angle increases, the tension in the rope increases, and we've already given the reason. So what this is showing us then is for an object on the ramp, the gravitational force, which is of course straight down towards the center of the Earth, that force has two components. There's one component that is squeezing us, pulling us down onto the ramp, and then there's another component that's pulling us, sliding us down the ramp. So this one I call the squeeze component, and this one I call the slide component. Now the slide component, you can put it down here to make a nice right angle triangle, and then that will make the finding components easier. But we should remember, of course, that it is actually pulling us down the ramp. Okay, so when you're on the ramp, gravity does two things. It squeezes you onto the ramp, and it slides you down the ramp, squeeze and slide. Now, of course, there's other forces that act on this object. There'll be a normal force. Now, normal, remember, means perpendicular. So the normal force in this case, perpendicular to the ramp. And then there can be friction if the surface is rough. Let's consider a couple of force diagrams then. So we'll draw a force diagram for an object that is on a rough ramp, so we know we have to include friction. And first of all, it's sliding down the ramp. If it's sliding down the ramp, okay, gravity, the Earth pulls down, normal force perpendicular to the ramp. And then if it's sliding down the ramp, then friction will be up. Now, while we're at it, we could draw in those two components of gravity. So there is the squeeze, that's perpendicular to the ramp. And there is the slide, that's down the ramp. Now, I should make that look like it's parallel to the ramp. There we go. And then we should also check that those make a nice triangle. Pretty good. That one's a little bit long. There we go. That should be a 90-degree triangle right there. Okay, so that's the force diagram when you're sliding down the ramp. Okay, now if you happen to be sliding up the ramp, then much is the same. There's still the normal force, the downwards weight, but if you're sliding up, then the force of friction will be down the ramp. So force of sliding friction is just opposite to the motion for the case of a sliding object. Okay, so that was sliding up, sliding down. What happens if the object is actually at rest? Well, we'll consider that in class. Now let's do a little geometry here. Okay, so here's the gravitational force, and those are its squeeze and slide components. And we want to be able to do the trig to find out what those squeeze and slide components are, right? So how much is that component, and then how much is that component if this force here is mg? Okay, this is mg. I'm not going to label it because I've got some numbers on here that I want to be clear. Okay, so we notice that this angle will be 90 degrees just because that's a perpendicular. So this angle up here, number 2, is 90 minus theta because they are complementary angles in a right angle triangle. Angle 3 equals angle 2 because they are what we call vertically opposite. So vertically opposite angles. Then angle 4 is 90 because that's perpendicular to the surface. And then angle 5 then must be theta. Because if this is 90 and this is 90 minus theta, then this angle up here has to be theta. So it turns out that this angle in the component triangle is always the same as the ramp angle. So the angle is always equal to the ramp angle. And then that means that we can find the components. This component here, this squeeze component, that's the adjacent side. So that will be a cos theta. And then this slide component is an opposite side, so that will be a sine theta. So when the ramp is angled at theta, there's mg cos theta squeezing you onto the ramp and mg sine theta pulling you down the ramp. Now, again, we do the triangle down here, but then we remember, of course, that, come on, where are you? We remember that this component here is actually pulling us down the ramp. That's what I was trying to do. Okay, so now we're ready to do a problem. So here we have a mass sliding down a frictionless ramp. So in that case, there's only two forces, right? There's just normal force and weight. Normal force is perpendicular to the ramp, so when you draw it, make it look perpendicular, make it look like 90 degrees. And gravity is straight down towards the center of the earth. Again, for gravity, make it look straight down, and then for its components, make this one look perpendicular to the ramp, and make this one look parallel to the ramp. I'll do it down here, and then I'll move it up. Well, I'm not having much luck. There we go. That looks better. All right, so now let's label those. So this is the normal force, and this is the gravity force. Those are the only two forces that act on the object. Now, we're going to resolve gravity into its squeeze component and its slide component. We do that by considering the triangle. And we note that we've just proven that this angle here is always the same as the ramp angle. So this is 25 degrees. Okay, so for a 2 kilogram object, mg is 19.6 newtons of force. So that's the hypotenuse here, 19.6. So the squeeze component right here, the amount of force that's pulling you down on the ramp, that's the adjacent side. So that's 19.6 cos 25 degrees. And this component here that's pulling you down the ramp, that's the slide component. That is mg, or rather, I'm sorry, 19.6 sine 25. I'm just going to use numbers here to be more concrete. So it's 19.6 sine of 25 degrees. Now we need to work those two out. It's just a simple bit of trigonometry. And then we need to remember, of course, that this slide component is actually pulling you down the ramp, okay? So that's the amount of sliding down the ramp force. This is the amount of squeezing onto the ramp force. Let me do the trig for you here. Okay, so we've got 17.76 newtons here, 17.76, I'll just round it to 17.8, and then the slide component was 8.3 newtons. Okay, so now we want to analyze the forces. Now we're going to use a tilted coordinate system here. Okay, so my y direction is going to be perpendicular to the ramp, and my x direction is going to be down the ramp. So in that coordinate system, y and x, in the y direction, the mass doesn't move that way. There's no motion perpendicular to the ramp. And because there's no motion, that means there's no acceleration, and that means the forces are balanced, or the net force is 0. Now, what forces act in that direction? Well, there's the normal force, and then there's the component of gravity. So those two have to balance each other. The normal force just equals the squeeze component. So we know there's 17.8 newtons of force of the ramp pushing up on us. Now, that'll be more important when we have friction. Right now, it's not going to influence our motion, because along the ramp, we can see in this x direction that we just have the slide component. So there is an unbalanced force. So I should say unbalanced, or force net, let's write it that way, is the slide component. So when we write net force is ma, it's the slide component of gravity that equals ma. So this is the 19.6 sine 25, or 8.3 newtons of unbalanced force on a 2 kilogram object. So we can see our acceleration will be about 4.15, 4.2 meters per second squared down the ramp. So this is how we're going to solve ramp problems. Draw the forces, resolve gravity into its components, okay, and then apply Newton's second law. So what changes if now you have a rough ramp? This is a mu equals 0.2 ramp. Well, not much. The procedure is still the same. We're going to draw the force diagram. So we have gravity acting straight down towards the center of the Earth. We have normal force perpendicular to the ramp. This mass is sliding down the ramp. That means friction is up. And let's label those. Normal force, mg, it's a 5 kilogram object. So there's 49 newtons of gravity. And then this is friction. Now we're going to resolve gravity into its components like we always do. Gravity is partly squeezing us onto the ramp and partly pulling us down the ramp. And these two should be perpendicular to each other. Now, whoops, just doesn't seem to like to grab onto those the first time. Okay, so there we go. Parallel, perpendicular. Squeeze and slide. If you want to refer to these in slightly more sophisticated terminology, you could call this the FG perpendicular and this the FG parallel if you wanted. So you might write that as FG perpendicular, but I just call that the squeeze. You can also, with our coordinate system here, right, with this being the y direction and this being the x direction, you could also call this one the FG y component if you wanted. These are all good notations. Anything will do. Now remember that the angle of the ramp is the same as the angle in the coordinate rectangle. So this is 35 degrees. So this hypotenuse is the mg, the 49 newtons. And so this is 49 sine 35. That'll be the slide component. And then the squeeze component is the adjacent side in the triangle. That's 49 goes 35. So I'll work those out and be right back. Okay, so that's 40.1 newtons of squeeze and 28.1 newtons of slide. So now let's analyze the forces in the y and x direction using Newton's second law. Now again, the mass doesn't fly off the ramp, it slides down it. So that means in the y direction there's no motion, zero acceleration. Zero acceleration tells us the net force is zero, or the forces are balanced. There's only two forces in that direction. There's only the normal force and the squeeze. In some problems, there'll be other forces to consider, but in this case, there's just those two. Those are the only things in the y direction. So there's 40.1 newtons of normal force. Now, that's important because now we can find friction. Now, in previous problems, on the flat surface, the normal force was always the same as the weight, but here it isn't. Here, the normal force is equal to a component of gravity. So we multiply the coefficient of friction by the normal force and we get 8.0 newtons of friction. Now we can consider net force along the ramp. Okay, so now in the x direction, we have two forces to consider. Let's move this one here so we can get a good picture of it. So now we've got 28 newtons down the ramp and we've got 8 newtons up the ramp. So we have the slide component minus friction is our net force in the x direction. You see, gravity has been resolved into its components, so it's almost like once the components are there, we're blocking this out of our mind, and we're just seeing Fn and squeeze in the y direction and friction and slide in the x direction. So net force is always equal to ma. What is it in this case? It's the slide component minus friction. There's 28.1 newtons of slide, 8 newtons of friction. This is a 5 kilogram object, so we can find its acceleration. So that's 20 over 5. That's 4.0 meters per second squared of acceleration. So this is an introduction to force analysis on the ramp. You should try now and do the first, let's see, up to E here. So this mass is moving up the ramp. Okay. Go through the steps in the previous problem, draw the force diagram, find the gravity components, normal force and friction, and then acceleration. Okay. After you've tried that, play the rest of the video where I go through the problem. Okay, so I'll just pause it right here, try this problem. Okay, so hopefully you were able to get this one started. All right, so here we've got weight, normal force, and then given that this one's sliding up the ramp, friction will actually be down. And we will resolve gravity into components just like usual. There is the squeeze component perpendicular to the ramp. There's the slide component down the ramp. Okay, so let's work out what those forces are now. So this is the force of gravity on a 6 kilogram object. That's 58.8 newtons. The ramp angle is 45, so the component triangle angle is also 45. Okay, so here we are, 58.8 cos 45. That's going to be our squeeze component. Let's see how much that is. That's 41.6. Now, our slide component, the 58.8 sine 45. Now, in a 45-degree triangle, it's isosceles. You can check if you want. It will also be 41.6 newtons of slide. Okay, now to find the normal force, which is our next task, we're going to analyze forces in the y direction. So here's our little coordinate system. Y direction is perpendicular to the ramp, and x direction is down the ramp. Remember, you can choose your own coordinate system. You can put it any way you want, but this is a convenient one for the ramp. So now let's analyze forces in the y direction and the x direction. Okay, so in the y direction, again, there's no motion, right? So that means acceleration 0 and forces are balanced. If they're balanced, there's only two. There's just the normal force and the squeeze component. So we know the normal force is 41.6 newtons of force. That helps us find friction, which acts in the x direction, because friction depends on mu and the normal force. The mu constant is 0.1, and the normal force is 41.6. So again, in these problems on the ramp, the normal force no longer equals the weight. So you have to use the correct normal force to get the correct value for friction. Okay, now, common mistake at this point in the net force equation. In the previous problem, the net force was the slide component minus friction. We subtract because they're opposite, and this one's bigger, so you subtract slide minus friction. Notice in this problem, pay careful attention to this though, that the slide component's down the ramp. Okay, that's always that way. But now friction is also down the ramp because we're moving up. That means the net force is going to be the sum of those two. So check your work and make sure you did that properly. Come on now, there we are. Back to here. So now it's slide plus friction that equals ma. So we've got 41.6 plus 4.16 equals the mass times the acceleration. So that is 46.8 over 6, and that's 7 point, well, let me check that here. So that works out to an acceleration of 7.6 meters per second squared. Now, if you look at the example, you'll see there's actually another part. It says find the time to stop. This mass has started moving upwards at 20 meters per second. That's given information on the picture. If it stops its final velocity at 0, we've just found the acceleration. So now we can actually do kinematics on this. Now, kinematics requires that we consider direction. And up and down are different directions. So one of these is going to have to be negative. I'll pick the initial velocity to be negative, because if you look in my coordinate system here, I was taking the x direction, the positive direction, to be down. Okay, so that means that this velocity is pointed in the negative x direction initially. Okay, so then I can just do kinematics. Vf is vi plus at. 0 is 20 plus downwards. Oops, I'm sorry. Upwards 20. Look at that, eh? Look at that. You could pick the other coordinate system if you wanted, right, and make the velocity positive and the acceleration negative, as long as you're consistent. It's important, though, that the time end up being a positive number. So we've just got to do 1 over x times 20, a quick way of doing division on your calculator, and we find 2.62 seconds to stop. Okay, so that's a few ramp problems to get us up to speed. In class, we'll do one together, then you'll work on some, and then we'll talk about some advanced incline problems. So that's our preparatory video for today.